In this project, I'll be talking about enzymatic reactions. My driving question for this was to test how changing the temperature of the substrate through the environment would affect the activity of catalase enzyme sourced from potatoes. To give context to the principles and concepts surrounding this project, catalase is an enzyme found in many living organisms. This protein acts as a catalyst in a biochemical reaction to speed up this process by lowering the activation energy required for the enzyme to bind to a substrate. In this case, catalase binds with the substrate hydrogen peroxide and produces water and oxygen as products. Enzyme activity to bind to its substrate is dependent on many external factors, such as pH. In particular, temperature has a strong influence on the function and shape of an enzyme. Enzymes have a unique shape with chains of amino acids that fold together. In the structure of an enzyme, there is a key lock mechanism that allows specific substrates to bind to it, giving it a specific function. In optimal temperatures, or in other words, the temperature most ideal and effective for maximum activity of an enzyme, this key lock mechanism allows it to easily bond to substrates, like a puzzle. However, as temperature increases beyond this point, the active site begins to denature or deform until it is unable to function normally. This process of denaturing and the concept of optimum temperature will be key ideas explored in this project. Having this background knowledge, the project will attempt to prove that enzyme activity will decrease after a certain threshold of temperature being too warm due to the principle of denaturing. The independent variable in this experiment will be the temperature of the substrate, hydrogen peroxide. The dependent variable is the time it takes for the recorded reaction to occur. And lastly, the controls include the catalyzed solution and the baseline test for how the catalase solution would react. Materials for this project include distilled water, hydrogen peroxide, cup potatoes, a small ice chest, a ruler, stopwatch, measuring spoons, gram balance, 5 jars, 1 large jar, ice cubes, a hammer, wax paper, coffee filters, a kitchen knife, tweezers, sealable bags, a blender, freezer, refrigerator, stove, thermometer, a cooking pot, and lastly, a lab notebook. To begin the experiment, we start by preparing the catalase solution. First, set 300 milliliters of water in the refrigerator for later use. Then, cut out 18 3x3 centimeter coffee filter squares and set aside. Next, fill an ice chest with ice and close it for later use. With leftover ice, crush 8 ice cubes into a gallon sealable bag and place it in the chest. With that set aside, peel raw potatoes into small pieces weighing out 50 grams for use. Bring back the distilled water and crushed ice in the bag and pour 60 milliliters of water, the potato pieces and 30 milliliters of crushed ice into a blender and mix for 20 seconds on high speed. Afterwards, transfer the solution into a large jar, stirring it through a coffee filter. Add an additional 150 milliliters of chilled distilled water into the large jar and thoroughly mix. Lastly, test the solution at room temperature to set a baseline for how the catalase solution should react. To do this, ready a stopwatch. Add 40 milliliters of hydrogen peroxide at room temperature in a 4-ounce jar. Using tweezers, submerge one of the pre-cut coffee filters into the catalase solution. Tap off any extra dripping solution and lower it into the jar and drop the coffee filter into the hydrogen peroxide. Upon immediate contact with the surface of the hydrogen peroxide, start the timer. Once the square has sunk and then reached the top again, stop the timer and dispose of the coffee filter. The coffee filter should have ideally taken around 20 seconds to react. With this, we can start to test the enzyme solution with the changing temperatures. First, test the solution at 0 degrees Celsius by pouring the hydrogen peroxide into a jar and placing it into the freezer to cool down to around 1 to -1 degrees Celsius. Then, test the enzyme activity by repeating steps 11A to 11G from making the catalase enzyme solution section and record how long it took for the square to sink and rise again. Next, test the solution at 10 degrees Celsius, repeating steps 1A to 1B, but this time putting the jar in the refrigerator. Once the hydrogen peroxide is between 9 and 10 degrees, repeat steps 1D to 1E. After completion, test the solution at 20 degrees by repeating steps 1A to 1B, but keeping the jar at room temperature. Once it is around 20 degrees, repeat steps 1D to 1E. For the fourth test, the solution will be compared at 30 degrees Celsius by cooling down water from near boiling. In a jar, pour hydrogen peroxide, then pour water into a cooking pot and heat until around 40 degrees. Place the jar in the pot and the gradual cool-off should even the hydrogen peroxide temperature to around 30 degrees, which is when you would repeat steps 1D to 1E. The last test at 40 degrees Celsius follows the same steps as 4A through 4B, except planting the hydrogen peroxide in the pot once the temperature reaches 60 degrees Celsius, and record data when it cools to 40 degrees. After first trial for all the temperatures is complete, repeat steps 1 through 5 for 2 more trials. Next, calculate the averages of the time it took for the reaction to occur for each temperature. And lastly, graph the results with data. When conducting this experiment, following the previously stated procedures, be cautious when handling boiling water and use all equipment appropriately. Adult supervision is encouraged if you are underage. Based on my results, as temperature increased from the starting point of 10 degrees Celsius, the reaction time became slightly faster, which is seen when comparing the 64 seconds it took for the coffee filter to sink and rise in test 1 of the second half of the procedure to the 6 seconds it took for test 4. The reaction time then peaked around 37 degrees, which is proven to be the optimum temperature for catalase enzymes. After that point, the reaction began to slow, as deduced to be from denaturing. To give a visual, these were images taken from my experiment. Image 1 was of the catalase solution. Image 2 was a picture of when the coffee filter sunk in the hydrogen peroxide, which contrasts to image 3, which shows when the coffee filter had risen to the top again, indicating the end of the reaction. For my 3 trials, the data table shows the averages from each test. The 5 increment benchmarks of 15, 25, 35, and 45 between the initial temperatures tested were estimates based on the trajectory of the graph to give a better sense of the gradual effect of temperature. Seeing the results, it was found that the reaction took longest at 10 degrees Celsius with 64 seconds, the shortest at 35 degrees Celsius with 6 seconds, and rose again at 40 degrees Celsius with 7 seconds. The line graph better shows these averages put together. The downward curve indicates faster reaction time as it gets closer to optimum temperature, while afterwards shows the time slowing. From this graph, we can conclude how the enzyme activity was the highest between 35 and 40 degrees since it was the quickest to react. In conclusion, the results and data collected proved the hypothesis to be correct. As predicted, rising temperatures cause the enzyme activity seen through its reaction time to slow, while temperatures going towards the optimum temperature were seen to increase the enzyme activity until hitting ideal circumstances. A key scientific principle and point of understanding for this project revolve around the concept of denaturing. This process causes enzymes to deform and distort their shape, often due to the influence of external conditions surpassing an enzyme's ideal circumstances. In this project, we observed these effects when looking at the change in enzyme activity based on different temperatures. When an enzyme becomes denatured, the active site is ruined and causing it not to be able to bind to a substrate. Thus, it cannot fulfill its function. When reflecting back on my experiment, problems that I encountered primarily consisted of making the enzyme solution itself so I could have reliable results that yield noticeable and identifiable changes when put up against varying temperatures. If I were to repeat this experiment, I would be more aware of specific measurements and act faster to ensure smaller margins of error influenced by factors out of my control, such as gradual denaturing of an enzyme. The concepts and ideas reviewed in this project can be connected back to life as it is seen all around us. There are many different types of enzymes in all organisms that assist in numerous processes but are only effective when under the right conditions. Take having a fever, for instance. Your body temperature becomes higher than normal, which changes the conditions of which some enzymes are in, causing them to slow and not be as reactive. Given this, the concept of how external factors affect enzymes can be further elaborated on if continuing this project idea, such as exploring the impact of pH. And that concludes my project.